you everybody, and good afternoon. So my name is Tero Sarkkinen. I'm a Finn currently living in Zurich, and I've worked in computer graphics industry for about 17 years, always with leading edge graphics performance measurement. Started from PCs, that was the time when PCs started to have graphics cards, and then went on to mobile phones, tablets, stuff like that, and then I did a 7-year gig founding a company that applied this graphics for automotive industry, still going very, very strong, called RightWare. And 1 year ago I separated one unit of RightWare into a own company called Basemark, and we are basically now focusing on AR and VR graphics. So I'm going to share with you some of our findings and some of our methodology, and hope that you will find it useful. So, first of all, why is this important? Well, we all know the old saying in gaming that latency kills, but in VR and AR it kills. So this is the real thing why this is very important. Everybody tries to get millisecond or shave off millisecond after millisecond in order to reduce the latency, because the moment when you break the illusion, when you turn your head or you move your body and things in the screen don't reflect what your brain expects it to reflect, then you start to feel sick. Yeah, we've had quite interesting stuff at our labs when we've been developing these tests, so we don't recommend you to watch those. Okay, but basically when we talk about VR, AR, there's a wide spectrum of different content and different applications, and very wide spectrum of the different sort of performance requirements for those. So if we start from the easy 360 pictures, 360 videos, you don't really need to have a very beefy system to view those. Modern top-end smartphone will do just fine. But then when you start to go into interactive real-time 3D graphics on, say, entry-level or basic VR and AR applications, then you really need to start to have a very high graphics processing power and also CPU. And then on the high end, well, sky's the limit really, as we start to see HMDs with the extremely fine FOV, with a huge amount of pixels, and you need to render for left and right eye, say 90 or sometimes even 120 frames a second. Calculate all of that in real time. That's a heck of a lot of pixels and performance required. And so then let's get some definitions. So what is latency and what we can measure out there. And so basically, many people want to measure the motion to photon latency. So that means like from the moment that I tilt my head, when is the appropriate new screen presented to my eyes, and measure that in milliseconds. But there's for application developers is usually good enough to measure the application to photon latency. And so basically how this whole process works is that I move my head or I move the controller, so then the HMD sensors detect that. They send that signal to the simulation system, so be that the PC when you're rendering on your PS4 or then the one embedded in your HMD. So the two first parts are HMD, but then there's an input-output, which is like how fast basically electricity goes to the simulation system. But then in the simulation system you usually spend the most amount of time. And so this is like getting the signal in, then calculating what the new image should be, and then rendering that new image, and then sending that new image to your HMD. So this is where the most milliseconds are sort of wasted. And so what to test? Oh, let's see. Very good. Let's see. I have one good slide and then not so good slide, I guess. This is very interesting. Let me try to. Okay, I don't have this one before. Okay, well, hopefully you can see. So, what to test in latency? So, first of all, we need to be aware of the HMD's psync limit. So, some devices have 90 FPS, that's what they expect. But they can drop to, say, 45 if the rendering system is not able to keep up. Yet again, some systems work at 60 FPS. So these translate, so 45 FPS means 22 milliseconds per frame, 60 is 17, and 90 is 11 milliseconds per frame. So there's not a whole lot of time for the system to do everything. So this can result then in drop frames. So basically, there was supposed to be a new frame shown, but it was never shown. And so this is a bad thing, of course. Then another sort of, I don't know, I wouldn't say anomaly, but okay. Technology is time warp that results in duplicate frames. So asynchronous time warp basically means that the system has calculated a larger image originally than it was needed for one frame, and then it detects a movement, and the system knows that it doesn't have time to actually calculate the new image, but it can approximate the required new image by taking it from the previous frame. And screen persistence is also a critical factor in the latency measurements, so low persistence usually provides a better experience. Another thing is the left versus right eye. So when you test for latency, you definitely need to measure both left and the right at the same time. You cannot just first measure left and then right, because you might have different anomalies rendered for either of the eyes. And then, of course, keep an eye on image quality. So when you test, some systems may try to get away with lesser image quality. And if you're really comparing device to another device, then you need to make sure that both are actually rendering the same image, not just that one is rendering with very low quality and one very high. That would work. Okay, well, so my company, we are in development of VR testing software and device. The software is in beta, but we've got the latency testing device. You can see pictures here. With the top one, which we are already shipping to customers, you can measure very reliably application to photon latency. And now we are developing a device on the bottom that we are able to then also take into account the motion to photon with that. But on the next slide, I'm going to reveal for the first time in the world latency measurements results for a couple of the most popular HMDs that there are out there. So here's the scoop of the day. So we measured OSVR, HTC Vive, and Oculus Rift. And you can see that the application to photon latency, even in the best one, is around 20 milliseconds. And so OSVR is the fastest in our tests. HTC Vive about the same, only 4% difference. But then there's quite a big gap to Oculus. And as you can see, Oculus already is 24 milliseconds. So this means that, according to this data, it's not able to render in real time exactly the frame that you need if it is to keep the required FPS. Okay, so then let's move to performance, or graphics performance. And in this area, basic old school measurements are the FPS, or frames per second, min, max, and average. But in VR, that's not the most important. In VR, the most important is that can you keep a steady say 90 or required FPS rate. And if you can't, if there's one frame that is dropped, then that might be okay, but heaven forbid if you got 2 in a row or 3 in a row, then you know the experience is totally ruined, and the person who's viewing the content will definitely notice that and breaks the illusion. And so then, as I mentioned, some HMDs, such like HTC Vive, they try to keep the 90 FPS, but if they detect that the system is not able to solidly keep it up, then they drop their VSync rate to 45. And actually this probably results in a better experience for the user, even a slower refresh rate, but if it's steady, then it's much better than higher with occasional spikes. And you can actually see in the lower graph over here, this is a real data from one of the devices. So you can see it's keeping up 11 milliseconds, so that means 90 FPS, and then occasionally there's some slowdown, and it goes to 22 milliseconds, and that's the 45.
Question.
Yes?
Is the top row with a monitor or without any display?
The top one is without the display, without the HMD. So that's like what is the actual raw output from the rendering system. So you can see that fluctuates. These are maybe from different systems, but anyways, that fluctuates there in the average is 6 or 7 milliseconds per frame. So that kind of a system should be able to provide the 90 FPS for an HMD. But then every HMD, they have their own SDKs. They do the image calculation, corrections and stuff like that. So they tend to have their own overhead. So basically, you always need to then have both parts of the system. But this enables you to dig a little bit deeper, like where the root cause might be. Okay, so how to do this performance testing? Well, of course, you're all welcome to use Basemark's products like VR Score. We are actually right now wrapping it up and expect to launch it within a month, but it's already available as a pre-purchase. Then there's independent testing labs such as TUV Rhino, who are very good at doing trustworthy testing, and they can also do certifications. And they are equipped with labs in 69 countries, so they can do motion to photon testing pretty much anywhere. And also my company offers to do testing projects, any type of custom testing in our labs. Okay, so then how to do performance optimization? Well, of course, you can't, unless you're one of the HMD developers, you can't change what's inside there, but you can of course choose the HMD that provides the least overhead for your system or the least smallest amount of latency. And the different SDKs versions for the HMDs, they do have different performance profiles, so you can also see which version actually works the best with exactly your application. And then, of course, the rendering system, well, if it's a PC, then anybody who's overclocker or gamer knows how to tweak systems or buy more and better and faster hardware. That usually solves things. But one thing is also system memory, to have enough and fast on. Because oftentimes, even if you got really beefy graphics, but your memory is not fast enough, then that creates some problems. But then then in the actual application, so first of all, if you are developing for consumer market, then of course you don't know what is the hardware that people are going to run your stuff on. But if you're developing for business application, then of course you should really optimize for that particular SoC or CPU, GPU combination. They have tremendously different profiles, so one programming technique works like a charm on one and then totally sucks on the other. So this is sort of a hand tuning of your code. These technologies like async time warp and multi-resolution rendering, AMD and NVIDIA respectively, so these are usually good in most of the cases. In some cases they provide outstanding performance improvement, and in some cases not so much, but usually it's a very, very good idea to use those. And of course then the graphics engine that you use, they differ quite a lot. We have been developing our test on top of CryEngine, so we know that that's pretty good. Can be recommended. And maybe then just there's a couple of resources for optimization, and you can then find more depending on your hardware target you're developing. For instance, Qualcomm and Imagination. So if you're developing for any iOS device, they have Imagination GPUs inside. So then pay attention to the Imagination resources. But these are very good and go into great depth, both AMD and NVIDIA. So very, very recommended reading over there. So, and then in closing, so basically what my company does in this area, so we are publishing soon, as I said, the VR Store. We are testing product, and that includes VR Track, which is the latency testing device. So this is an easy to use device for anybody, so it's relatively inexpensive, and you can use it without lab training. So even I can use it, I'm not an engineer. And then we provide and license graphics engine, rock solid, for demanding mission-critical VR AR rendering. Very lightweight and optimized for embedded applications. And of course then we can help and fine-tune your application, your code. Well, we come from a background of 17 years of graphics fine-tuning, so we know a thing or two how we can get the pixels flying faster on your screen. Alright, so that's it.